We move on to the second section, which is convolution. Below you can see x of n convolved with h of n, and we have a convolution operator in between. We have four subsections in this section. We start with the first of them, Introduction to Convolution. Consider an input signal as delta of n in the impulse signal, and you get the output as h of n. Another time shifted impulse signal, you get another output signal when passed through the system. And similarly, other input signals which are time shifted gives you other outputs. Well, these outputs are known as impulse responses. But what happens when you add all of these impulse signals? You get a discrete time signal defined at various values of n. Let's look what happens when a function is multiplied by an impulse function. For example, x of minus 1 times delta of n plus 1 exists for only n equal to minus 1, which gives you x of minus 1 for n is equal to minus 1, and similarly for other values. So we can write x of n as a summation of shifted impulse functions multiplied by the function value at that point, which we are going to use in the next slide. An LTI system is a system which is both linear and time invariant. So when you pass an impulse function or an impulse signal through an LTI system, you get the impulse response. And we know that any function x of n can be written as a summation of shifted impulse functions multiplied by the function value at that point. So when we pass any function x of n through an LTI system, we get a similar output signal y of n, which gives this expression, which we call it as the convolution sum, and this is very important equation. Now we know the output signal of an LTI system for input signal x of n and impulse response h of n, which is given as y of n equals x of n convolved with h of n, and we have a convolution operator in between. So we can find the output signal of an LTI system for any input signal given that we have the impulse response. And y of n is given as the summation k tending from minus infinity to plus infinity x of k times h of n minus k. We have so far considered only discrete time signals. Now considering the CT signals or continuous time signals, we find the convolution as this integral y of t equals integral of x of tau multiplied by h of t minus tau d tau, and the limits are from minus infinity to plus infinity. This is the convolution integral in the continuous time system. We now try to understand convolution with an example. Consider an input signal x of n and an impulse response h of n. We now need to convolve x of n with h of n to find the output signal y of n, and it is given by this expression y of n. So if we could find 0.5 times h of n and add it with 2 times h of n minus 1, we could find the value of output signal for any value of n. Using the h of n graph, we sketch 0.5 times h of n and 2 times h of n minus 1 and add both to find y of n. So now we have the graph for y of n. The next subsection is properties of convolution. Convolution shows commutative property for both continuous time signals as well as discrete time signals. So x of n convolved with h of n equals h of n convolved with x of n. Convolution also shows distributive property. X of n convolved with h1 of n plus h2 of n equals x of n convolved with h1 of n plus x of n convolved with h2 of n. Now this is a useful property because instead of using two systems with impulse responses h1 of t and h2 of t, we could use just one system with impulse response h1 of t plus h2 of t to get the same output. Convolution also shows associative property. So x of t convolved with h1 of t convolved with h2 of t equals x of t convolved with h1 of t convolved with h2 of t. Now, this brings to the conclusion that the order in which the systems are kept doesn't matter. So, if you have a system with impulse response h1 of n, you keep it before a system with h2 of n, you get the same output for the same input if you keep the system with h2 of n before the system with h1 of n as the impulse response. We now know that this is the expression for convolution sum. And now if we need to find the sum of all the outputs y of n, we put a summation. And we find that after all the calculations that sum of y of n equals sum of x of n times sum of all values of h of n. Our next subsection is LTI system properties. After all the calculations, we find that for an LTI system to be memoryless, it has to satisfy this condition h of n, that is the impulse response, equals k times the impulse function. So the impulse response exists for only n equals 0 and the value equals k, which is some constant. And in continuous time, the system has to satisfy this condition to be memoryless. If k equals 1, the systems are identity systems, that is x of t equals y of t. For an LTI system to be invertible, we find that the impulse response of this system, that is h of t, and the impulse response of the inverse system, when convolved, give you the impulse signal, that is h of t, convolved with h1 of t gives you delta of t. For an LTI system to be causal, it has to satisfy this condition, that is the impulse response equals 0 for negative values of n in discrete time and h of t equals 0 for t less than 0 in continuous time. So if the impulse response is a causal signal, we say that the LTI system is a causal system. Talking about the stability of LTI systems, an LTI system is stable if the impulse response is absolutely integrable. That is, it satisfies this condition for discrete time systems. This is the last subsection of this section, which is differential and difference equations. We'll try to understand differential and difference equation with examples. Well, the first example is in continuous time and it is a differential equation. The second example is in discrete time and it is a difference equation. Well, the output in these examples are not explicitly mentioned as a function of the input. So we need one or more auxiliary conditions, you could say initial conditions, to solve these equations. It is more like finding C in integration.